Okay, so today we're going to look at measuring tools and how they're used, and we're going to measure the density of this metal cube right here. So on the left side, we see a normal millimeter ruler, and it's broken up into centimeters, which are the larger graduations, and then each of those is broken down into millimeters. So the last readable digit on this guy is millimeters. Over here, we have a micrometer, and it can actually measure to the nearest tenth of a millimeter. Sorry, hundredth of a millimeter. Okay, so the last readable digit on this guy would be 0.01 or 1/100th of a millimeter. Now, we're not actually going to use this, but I just wanted to bring it up here for demonstration purposes. If we were to use this to measure our the sides of our cube when we're finding its volume, we would get a much more accurate value, or a value down to a smaller unit. Unfortunately, this isn't going to fit on here. It's just not big enough. And for our purposes, this is just fine. Okay, so the first thing we're going to do is we're going to measure our sides. So I'm going to zoom in a little bit so you can see exactly what I'm doing here. Okay, so I'm going to put my ruler on there, and I'm going to measure this side of things. Okay, so right there, what you can see is that for digits that I can actually say I know for sure, I know it's at least 3 centimeters long, and I know that it's somewhere between 3.1 and 3.2 centimeters. Okay, you can clearly see that it's just under halfway between 3.1 and 3.2. So I'm going to mark down that this is 3.1, and then I'm going to estimate about where I think it is between the 0.1 and the 0.2, and it looks to me about maybe 4/10 of the way across. So I'm going to say that this side measures 3.1 and then estimated 4 centimeters across. Okay, so 3.14 centimeters on that side. This digit is known, this digit is known, this digit is estimated. Okay, if someone else came along and they were to, take the same measurement that I just did, their value for this might be slightly different from mine. They might think it's halfway between and put 3.15. They might think it's 3.13, but I think we would all agree that it's somewhere between the 0.1 and the 0.2. Okay, so this is how you read an analog ruler. Okay, with this thing, there's actually another way to read it, and you would actually read off the dial. It's very unlikely that we would ever need to use something like this in a standard physics course, but I mean, it's possible. And just to let you know, there are things out there that can measure more finely than my ruler can. Okay, now I went ahead and I measured all the sides, and I actually found that this is a pretty well made cube, and each side is exactly the same dimension. Okay, in reality, you're probably not going to find something that's absolutely perfect, and if I used my micrometer, I might find some variation, but with the ruler that I have, this is what I found. Now, because this digit's estimated, we have to also include that there's some uncertainty in each of our measurements. Okay, so we're going to add that on as half of the last readable digit. So if you remember, our last readable digit was 1/10 of a centimeter or 1 millimeter. Okay, so what that means then is that our uncertainty is going to be plus or minus half of that digit. So just like that, in terms of centimeters. All right, so we're going to add that on to each one of our values, plus or minus 0.05, plus or minus 0.05, and plus or minus 0.05. I'm not sure exactly what convention you're supposed to put. This would be fine. I think this would also be fine. Or even probably 3.14 plus or minus 0.05 centimeters might cover it all. That's sort of irrelevant as long as you're indicating to the reader what you're talking about. Now, what does this really mean? It means that I am somewhere between 3.19, right? I'm adding the 0.5 on the plus side, and I'm subtracting it on the low side, and I guess 2.99? Yeah, 2.99 centimeters on each side. Okay, so that's my uncertainty. let's just double check that. No, not 2.99. 3.09 there. That's what I want to say. 3.09. Okay, so it's somewhere between these two values, 3.09 and 3.19. Nobody probably who has two eyes in their head and kind of knows how to use a ruler would probably ever think that it's outside of this range. So this more or less accounts for any uncertainty. Something to notice is that no matter what value I get for these, this will never change on a centimeter ruler. Okay, and then the uncertainty on this, of course, would be half of the last readable digit. So if we went back up here, you're actually going to look at 0.0005 for this guy. Okay, so there we go. Now what do we do with this? So the first thing I want to do, if I'm going to find a density, is I want to find out what the volume of the original cube was. So I'm just going to take out my calculator, and I'm going to sort out what the volume is. Okay, so I'm going to take each side, and I'm going to multiply it by itself 3 times. I'm going to get something that looks like that. Now, there's a problem with this, and the problem is this. The calculator doesn't know that I'm dealing in centimeters. It just takes the numbers I put in and gives me the remainder. It gives me the decimals that come with it. Okay. But what this is telling someone, if I leave it like this, is that I know this to the nearest cubic millimeter, or tenth of a cubic centimeter, hundredth, thousandth, 10,000th, 100,000th, and millionth. I'm saying to them, if I leave it like this, that I know that the volume of this is measured to the nearest millionth of a cubic centimeter, which of course is impossible considering the fact that I started with a 25-cent ruler. Okay, so to take care of that, we have to do some rounding. All right, if I just wanted volume, and that was the end of this lab, right now I would count 1, 2, 3 significant digits here, and realize I can only put 3 significant digits there, and I would get this value. Okay, so I look to here. This is going to round up, and then this is going to round up. So my value would be 31.0 centimeters cubed. I need to leave the 0.0 to indicate that I am certain of this digit. We do need 3 significant digits. Any 0 past the decimal is significant. So we're saying we know this value, we need a placeholder there, even if it happens to be 0. Okay, so that's the rounded value for volume. However, since we're finding a density, I'm just going to hang on to this number for now. Okay, to find a density, I need mass per unit volume. Okay, so I need to go ahead and find a mass, and I already did that, and I'll just pull it up real quick. Okay, so I used a digital scale to find mass, which also brings up a kind of an interesting thing. With digital tools, there's a slightly different way of dealing with that uncertainty. So my mass comes out to 247.2 grams, and on a digital unit, it's just plus or minus the last readable digit, so plus or minus 0.1 grams. Okay, so this is 247 plus or minus 247.2 plus or minus 0.1 grams. Okay, just keep that in mind that digital is a little bit different. So there it is, 247.2 plus or minus 0.1 grams. So what we're really saying is this can only tell us that it's somewhere between 247.3 and 247.1. And if you think about it, it should make sense to you as to why we can only for sure say that. And the reason, of course, is because this number, what's shown here, depends on values that come after it.
Musical theater graphic students, please report to the math lab, room 119 right now. All musical theater graphic students, please report to the math lab, room 119.
Well, thanks for the interruption from Mr. Shoesmith. And moving right along. Okay, now, to find a density, we of course take mass in grams and divide it by the value that we got for volume. You'll see here that I'm putting all my decimals in, okay? And we don't want to round all our numbers that we're going to use later, because then we're going to introduce some rounding error. So 247.2 divided by 30.959144, and we get 7.98. 471,689, which of course, again, as for reasons explained before, is way too many numbers. Now if we look and see, way back to the start, in our initial numbers, 3 significant digits is all that we can show. So we need to round off to 1, 2, 3 significance, and we say these are insignificant because we do not know them for sure. Okay, that's just a product of the way that the calculator does math. So 7.98 grams per cubic centimeter is our value for density. However, one thing that we haven't accounted for is all of this uncertainty. So the way to do that is you actually have to find the percentage uncertainty in each of these values. Okay, percentage uncertainty is fairly straightforward to find. What percentage of this value here is the uncertainty? So to do that, 0.05, that's our uncertainty. What percentage of 3.14 is it? And it's just a standard percentage calculation. So we get 0.05 divided by 3.14 times 100, and we get 1.5923 and change. I'm happy if there's 3 significant figures here, if you use 3 significant figures in your uncertainty calculations. So it's plus or minus 1.59%. All right, so all the way along, each of these, since they're all the same, has 1.59% uncertainty in them. So in our volume calculation, going back over to here, we would have 1.59, about 4.77% uncertainty. Okay, so our volume calculation here is plus or minus 4.77%. I didn't really leave myself enough room, but to illustrate what I'm talking about, I'm just going to put it over here, right? So remember, every time we multiply, we have to bring in the percent uncertainty that each of those measurements brings to the table, and they have to add up together. Okay, so the volume calculation brings with it 4.77% uncertainty, and let's see what this one does. So 0.1, this is going to be obviously much, much less uncertainty. Almost probably an insignificant amount, but let's see, divided by 247.2, and it's about 0.04%. Okay. But when we divide, we also have to bring along our uncertainty, so we have to add that together. So what we're going to say at the end here is it's plus or minus 4.77 plus 0.04, so 81. Okay, so 7.98 grams per cubic centimeter plus or minus 4.81%. The last step is to take this and convert it back into the units that we're dealing with. So to do that, 7.98, what number is 4.81% of 7.98? 4.81% would look like that. And the value we would get about 0.38. We write our final value for our density as this, 7.98 plus or minus 0.38 grams per cubic centimeter. Now the value that I found in a book for iron is actually 7.874 grams per cubic centimeter. So we're pretty close. In the next video, we'll look at how do we check how close we were, and is our number something that's acceptable, or is it outrageously off? Okay, that's for the next video.